In this next section, let's consider the Earth as a planet. So if this is the Earth as a planet, one of the things we know about it is that if you're standing on it, it's going to exert some sort of gravitational force on you. So that's fine. We know the Earth has a radius. And the Earth has a mass. We'll get to those values in a second. But let's say you were standing on this Earth here, obviously not drawn to scale, but just for fun. And you're holding a ball and you drop the ball. Does the ball fall? Of course it does. Does it accelerate down? You better believe it. Because what are the forces on the ball? If you were to draw a force diagram on this ball, you would see that the force on the ball is equal to mg. We call that the weight of the ball. It's the mass times the gravitational field strength near the surface. We have a sense that this is around 10 near the surface of the Earth. But what I like about this is this here, this mg, is also the gravitational force on the ball in terms of Newton's law of universal gravitation. So what we can say here is that this little fg, F by the gravitational field, is also equal to the universal gravitational force developed by Newton. So we express this like this, where the F little g, the force by the gravitational field, that's this one, is equal to Fg, Newton's law of universal gravitation. What I think is really interesting about this is what happens when you plug these in here. So we're talking about this little ball. So this is mg, that's the mass of the ball times the gravitational field strength. Here, again, Newton's law of universal gravitation is universal gravitational constant times the mass of the Earth times the mass of the ball, all divided by r squared. Now in this case, r is really the distance. It's going to end up being the radius of the Earth because in this case, r is the distance from the center to the surface, and the height of the ball, although my picture is not to scale, is really the same. So when I look at this, I would say, well, what m is this? This is the mass of the ball, but the mass of the ball is over here also. So do these masses magically disappear? They totally do. And we end up with this cool expression. The gravitational field strength is equal to g times the mass of the Earth, all divided by r squared. And this r is the radius of the Earth. Now, this is for the Earth specifically. So let's see what happens here. If I want to calculate this, let's use the universal gravitational constant, 6.67 times 10 to the negative 11, times the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. And then we're going to divide that by the radius of the Earth. .37 times 10 to the 6th meters. Now, this is an inverse square relationship also, which is going to end up being important. If you put this in your calculator and you plug and chug it, you get g is equal to 9.87. Now, the units here can vary. Okay, it's either newtons per kilogram if you are calculating the gravitational field strength, but in this case, because our ball was accelerating, we could say it was also equal to meters per second, or meters per second squared. And this is exactly what we expect. It's close to 10, it's a little bit less. We use 10 in the classroom, the textbooks use 9.81. I'm pretty happy with that. The thing I like about this equation is that it's generic. You could use it for any planet. We could say that the acceleration due to gravity or gravitational field strength on any planet is equal to the universal gravitational constant times the mass of that planet divided by the radius of that planet squared. So this generic form allows us to understand things like what you would weigh on Venus, what you would weigh on Mars, what you would weigh on Jupiter if it had a surface at a radius. And that's an interesting way to express this, but this generic form is important. Oftentimes you'll get a question that says, oh, well, at the surface of the Earth, for example, at the surface of the Earth, the gravitational field strength is around 10. What would happen if you went out not one radius to the surface, but what if you went out a whole extra radius out here? Let's say you're in a satellite. What would the gravitational field strength be out here at 2 radii away? Well, at the surface, G is equal to about 10. That's 1 Earth radii. But if you got to 2 Earth radii, what do you think the G value is? Well, you are doubling the radius, so you're increasing the radius, so the G has to go down, and since it's squared, 2 squared is 4, so it goes down by a factor of 4. So this would be 10 over 4, which is about, what do you think, 2.5? So we have this sense that we can compare the gravitational field strength on the surface to the gravitational field strength other places. One of the favorite questions says, oh, well, here you are, you're in a, let's say the International Space Station, and you're in low Earth orbit, where we see the astronauts and they look like they're floating around. What is the G value in low Earth orbit? The thing is that if you look at this distance to the surface, we know it's 10, it's still a little bit farther. What do you think it is? It's 9 meters per second per second. That's the acceleration there. And they feel weightless for another reason. We'll have to talk about that another time. How does this manifest on a test question? Well, if you want to, the way it manifests on a test question, oftentimes it'll say, oh, well, now you have found yourself on a new planet, and what it does is it gives you a comparison. It says, oh, you're on a new planet. So let's talk about this new planet. They say, on this new planet, the mass is equal to 4 times the mass of the Earth. But the radius is equal to 4 times the radius of the Earth. It says, what is the G value on the new planet? So it has 4 times the mass and 4 times the radius. Now, you might be tempted to say, like, oh, well, if both of these have changed by a factor of 4, maybe it's the same. I'm not really sure it is. Let's look at the structure of the equation a little bit more deeply. So we know that you want to calculate this little baby G value, whether it's the free fall acceleration or it's the gravitational field strength. We know it's equal to big G times the mass of the planet divided by the radius of the planet squared. Now, what do we know on Earth? On Earth, it's equal to big G times the mass of the Earth divided by the radius of the Earth squared. So can I substitute some of these into here and help us kind of figure out what the situation is? So let's try that and see if that makes any sense to us. I want to go with G for the new planet here. We know it's equal to big G times, well, what's the mass of the planet? The mass of the planet is 4 times the mass of the Earth. So I'm going to say 4 times the mass of the Earth. What am I going to do? I'm going to divide by, well, what are we saying here? What is the radius of the planet? It's 4 times the radius of the Earth. So 4 times the radius of the Earth, but don't forget you need to square that. Now, if you're watching closely, you can see something interesting is happening here, where we're ending up with some stuff that we already understand. Here I have G times the mass of the Earth divided by the radius of the Earth squared, and then what am I multiplying it by? Well, what was my coefficient on top? Times 4 on top, but what did I do to this 4 on the bottom? I squared it, 16. If you look at this, g me over re squared, don't we have this here? We totally do. So rewriting this, I have the mass or the gravitational field strength on the planet is equal to 4 over 16 is 1/4. This whole thing is g on Earth. And so, what do we say here? The gravitational field strength on the new planet is 1/4 what it was on the Earth. You know, this is 1/4 of, we're going to say it's 10, which is, 1/4 of 10 is 2.5 meters per second per second. That's the kind of problem that you will see on your AP test.